Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Jest, Tifr, IIT-Jam and other exams related to physical science. Okay. So this is the lecture number 20th of quantum mechanics, in which we are going to discuss perturbation theory. Okay. It's a very important. You will get lots of questions in your examinations. Okay. And also I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live classes which are going to help you to crack the exams related to physical science. Okay, so I'm going to start now. Before start just before starting the class, I just would like I'm just going to check the sound whether I'm audible or not. Okay, let me just check it. Physical science. Okay, yes, I am audible, so I'm going to start now. Okay. Okay, so perturbation theory. Perturbation theory. Okay, perturbation theory. So perturbation theory is approximate method. It is a method, right? Approximate method to solve the Hamiltonian of the system. Okay, so it is an approximate method. Approximate method. It is an approximate method to solve Hamiltonian of the system. Okay, so it is an approximate method to solve the Hamiltonian of the system. Okay. Second is we can find out we can find out small correction terms, small correction terms in the energy of system, in the energy of the system. Okay, so we can with perturbation theory we can find the correction in the energy of the system. Okay, well, so the Hamiltonian after perturbation is denoted by H equal to H naught plus lambda HP. Okay, so where H naught is actual Hamiltonian of the system, actual Hamiltonian of the system. Okay, and H equal to total energy of total Hamiltonian. Okay, total Hamiltonian of the system, Hamiltonian of the system, total Hamiltonian of the system, and HP is the perturbation part of Hamiltonian. Okay, perturbation part of Hamiltonian. Okay, so this is a, so in this equation, this is total Hamiltonian of the system. This is actual Hamiltonian of the system. This is the total Hamiltonian after perturbation. Okay, and HP is the perturbation part of the Hamiltonian. Okay. Okay. Next point. So perturbation are of two types. Okay, time independent perturbation and time dependent perturbation. Okay, perturbation, time independent perturbation, time independent, time independent perturbation, and number two, time dependent perturbation. Okay, so perturbation is of two types, time independent perturbation and time dependent perturbation. As of now, we are going to study time independent perturbation. Okay, well, so here wave function psi n, wave function psi n we can write as lambda 0. Okay, lambda 0 psi n naught. Okay, plus lambda 1 psi n 1. Okay, plus lambda 2 psi n 2. Okay, plus so on. Okay, so any wave function can be written like that. Okay, and also we can write energy eigenvalue or energy of the system as lambda naught en equal to lambda naught en 0 plus lambda 1 en 1. Okay, plus lambda square en 2 plus 1. Okay, this one. Next, so now we know the time independent Schrodinger equation. Time independent Schrodinger equation. Okay, so that is, we know that is H psi n equal to E psi n, En psi n. Okay, so this we know. So this is the value of psi n. We can write like this: lambda naught psi n naught plus lambda 1 psi n 1, lambda 2 psi n 2, and energy is lambda naught En naught plus lambda 1 En 1, lambda 2 En 2. Okay, so now we'll use Schrodinger time independent equation. Okay, so so this equation is going to be, we'll put the value, right, because we know we have this one, equation 1, right, this one, H equal to H naught lambda HP, right? So we can write in place of H, that is H naught plus lambda HP. This is perturbation part of Hamiltonian, this is actual Hamiltonian, this is complete total Hamiltonian H, right? And the wave function, we can write, wave function is this one, psi n is this lambda naught psi n naught plus lambda 1 psi n 1 plus lambda 2 psi n 2 plus so on equal to we can write En psi n, right? So En psi n is going to be lambda naught En naught plus lambda 1 En1 plus so on, and this is psi n is going to be this one into psi, this is lambda naught psi naught lambda naught psi n naught plus lambda 1 psi n1 plus so on, right? So what we have done is we have just put the value of psi n and en and hn, right? So we've got this equation. Right now what we'll do, we'll compare both sides. Okay, comparing both sides, comparing both sides. Okay, okay, comparing both sides, we'll compare it. So this is going to give we are going to get values of first order correction. Okay, after comparing, okay, first order correction. Okay, first order correction, this one, this is the one, and first order, we compare it, right? So first order correction is going to be this one. Sorry, zeroth order correction, my apology, that is zeroth order correction. First zeroth order correction. Okay, so that is going to be h naught psi n naught equal to en naught psi n naught. Okay, psi n naught, and from here h naught psi n naught equal to we have compared the powers of lambda, right? So this is e naught psi n naught, right? So this is h naught psi n naught equal to en naught psi n naught. Okay, so this is known as, which known, this we know, that is known solution corresponding to actual Hamiltonian, right? Known solution corresponding to known solution corresponding to actual Hamiltonian. Okay, known solution corresponding to actual Hamiltonian, because this we know, right? Now first order correction, first order correction that is first order correction is this one, en en1 psi n1, right? First order correction. So this is going to be this is en1 first order correction is psi n naught hp. We have compared from here. Okay, from there, this. So h1 naught, sorry, psi n naught hp psi n naught, expectation value of this, right? So this is the first order correction in energy. Okay, so this is very important formula you need to know, or you need to note down. So this is psi n naught hp, that is the perturbed part of the Hamiltonian, and psi n. Okay, so this is the first order correction, and first order correction in energy. Now first order correction in wave function is going to be psi n1, and this is going to be sigma m not equal to n, okay, mod of expectation value of psi m naught HP psi n naught psi n naught. So psi m naught HP, there is perturbation part, psi n naught upon En naught minus Em naught. Okay, En naught minus Em naught. Em naught. Em naught. And here psi m naught. Okay, so this is the first order correction in the wave function. Okay, so psi m sigma m naught equal to m mod of psi m HP psi m naught HP psi n naught upon En naught minus Em naught into psi m naught cat of psi m naught. Okay, this is the state. This is the first order correction in the wave function. I hope you understood guys. Okay, next. Next is second order correction. Okay, second order correction. Second order correction, and that is En2, second order correction in energy. So the En2 value is going to be sigma m not equal to n. Okay, m not equal to n mod square of psi m naught HP psi n naught. Okay, mod square of psi m naught HP psi n naught upon En naught minus Em naught upon En naught minus Em naught. Okay, so m naught equal to n mod square of psi m naught HP psi n naught upon En naught minus Em naught. Okay, so this is the second order correction in the energy. Okay, second order correction in the energy. Okay, very important formulas these you need to note down and practice questions related to this formula so that you can remember all the formulas. Okay, well, this is the second order correction in the energy. Now we will study one dimensional harmonic oscillator. Okay, and so we'll perturb that one dimensional harmonic oscillator and then we'll see the effect of that. Okay, and then we will find out the corrections in the energy and wave function. Okay, so the heading is 1D harmonic oscillator. 1D, very important guys. Okay, harmonic, 1D harmonic oscillator. Okay, one D harmonic oscillator. Okay, actual Hamiltonian. Okay, so actual Hamiltonian, actual or main. Okay, actual Hamiltonian, actual Hamiltonian or mean Hamiltonian H naught equal to we know actual Hamiltonian of 1D harmonic oscillator, that is T plus V, and that value is uh, P square upon 2m, P square upon 2m, or Px square upon 2m. In 1D we are talking about 1D, right? px square upon 2m upon half kx square, right? This is the actual Hamiltonian of the harmonic oscillator. Now we'll perturb that harmonic oscillator and then we'll see the effect, okay? And then we'll find out the first order correction in energy and wave function, and second order correction in energy. Okay, so this is the actual Hamiltonian. Now we have applied external electric field, okay? If external electric field is applied, external electric field is applied, external electric field is applied, then energy correction, okay? Then energy correction. So we have applied external electric field, okay, very small, and that is, we know that is Fx, right? Energy correction is Fx, force into distance, right? So this is going to be Fx because electric field is applied, right? F equal to QEx, right? So this is the QEx and this is the perturbed part of Hamiltonian, okay? So this much of Hamiltonian, right? This is the perturbed part of Hamiltonian, okay? Because of system is perturbed, right? HP. So now new Hamiltonian after perturbation, new Hamiltonian H is going to be H naught plus HP, right? So H is going to be Px square upon 2m, okay, plus half Kx square plus HP value is QEx, okay. So this is the new Hamiltonian after perturbation of simple simple harmonic oscillator, right? Now we will solve it, simplify it further, okay. So this is going to be H is going to be Px square upon 2m plus half Kx square, okay. So this is going to be half Kx square, or half K will take common, okay. Half K we have taken common. So this is going to be x square will remain here, and here this is going to be 2QE upon K, 2QE x upon K, right? This will be the term here because K will get cancelled, 2 will then will get QEx, right? So simple step. So we have taken K common, okay. Next is this one. So now we'll make it in the form of this form, right? Only this form. Solve it. So this is H is going to be Px square upon 2m, Px square upon 2m plus half K we have taken common. So we have x square, this is x square plus 2QEx by K, 2QEx by K, 2QEx by K. So we can do one thing, we can do like Q square E square upon K square, we can add, minus Q square E square upon K square, we can subtract, we can do it, right? Because this term is going to be whole square, perfect square, and so if you're adding something and subtracting something, then this is not going to affect the expression, right? So Q square upon K square, right? Now H is going to be, it's just a calculation, okay. Px square upon 2m plus half K. So here this is going to be x plus QE upon K whole square, right? If you open it, we'll get this value, okay. And this is going to be minus Q square E square by K square, okay. Now we'll simply simplify it further. So this is going to be h equal to px square upon 2m plus half k into x plus qe upon k whole square minus, will multiply this, so this is going to be q square e square upon 2k, right? K will get cancelled, so 2k. Okay, this one. And now we can write like this. So h is going to be px square upon 2m plus half k x dash square. We can write this term, we can let say x plus qe upon k is x dash, right? Half k x dash square we can write, and minus this is going to be uh, q square e square upon 2k. Okay, this is the one. Okay, this is the value of px h, okay, for Hamiltonian after perturbation. H equal to px square upon 2m plus half k x dash square plus minus q square e square upon k square. Okay, okay, just let me check. Okay, so now we can, so now this is one, right? So here we can write that this is this Hamiltonian, this one. This is this tells that in absence of electric field, this we know, in absence of electric field, that is perturbation. Okay, in absence of perturbation or electric field, the mean position was at origin. Okay, the mean position of harmonic oscillator, mean position uh, of harmonic oscillator was at origin. Okay, origin. I will draw the figure, then it will clear your doubt. Okay, so in absence of electric field, the mean position was at origin. Mean position of harmonic oscillator was at origin, and but after application of EF, after application of EF, that is electric field, the mean position, the mean position, the mean position, the mean position uh, is shifted at x equal to minus qe upon k. How? I'll tell you. So here we know this x dash equal to x plus q upon k, right? Since x dash equal to mm, x plus qe upon k, x plus qe upon k, right? This is the x dash, right? So this implies value of x. So here the value of x equal to minus qe upon k, right? From here, right? The application of or after the perturbation, the mean position is shifted at x equal to minus QE. By diagram, I'm going to explain like this. Okay. So initially, the harmonic oscillator is like this. Okay. At origin, mean position of harmonic oscillator is at origin. This is not looking like this. Very sharp looking. Like this. This was the position. The mean position was here, right? But after perturbation, electric field, application of electric field, right? So this becomes like this. Like this. Okay. So position, it is 0 0, right? Now position comes here, minus QE upon K. Okay. Because after this the mean position is changed to x equal to q, changed to x equal to minus q upon k. But before perturbation, it was at origin. This was the diagram of simple harmonic oscillator before perturbation, dotted one, and this one is the this one the graph of simple harmonic oscillator after perturbation. So it shifted to minus QE upon k. Okay, I hope you understood it. And now the frequency and time period, the frequency and time period, of oscillation will be same. Only mean position will get changed, but the frequency and oscillation, right, the frequency and time period of oscillation of that simple harmonic oscillator will remain same. Okay, will be same, will be same. Only mean position will be shifted. Okay, that's I told you. Only mean position will be shifted, will be shifted shifted by QE upon K. Okay. Now so now we have this. Now then energy is going to be, En is going to be, energy of the perturbed Hamiltonian is going to be this one, right? We have this one, px square upon 2m plus half k dash x square. So this value is going to be this one is we know, right? That is n plus half h cut omega, right? And there is one more extra term, that is minus q square e square upon 2k, minus q square e square upon 2k upon 2k. Okay, so this is the after perturbation, the energy eigenvalue, energy of the system is going to be this uh, n plus half h cut omega minus q square e square upon 2k. Okay, or we can put the value of k. So this is going to be En equal to n plus half h cut omega minus q square e square upon 2m omega square, 2m omega square, because we know omega equal to root k upon m. So we'll square it both sides, then value of k is going to be m omega square. So in place of k, we have put m omega square, right? So this is the correction. Okay, this is the energy after perturbation of simple harmonic oscillator. So we have perturbed that, and then we measured the energy, and this energy is this. Okay, well, next point. Next is delta E. So now we find delta E, right? So En is this, delta is going to be En plus 1, we can find out, minus En, and we can see that is h cut omega. En plus 1 minus En, and that value is h cut omega, right? So if you put En plus 1 here, and if you substitute the energy En plus 1, right? Substitute En from En plus 1, so we are getting h cut omega. So what it says is decreasing, but there is no change in energy separation between the levels. So we can see h cut the delta we can see there is no change in energy separation. Energy separation between level is same as h cut omega, right? Which is for the actual Hamiltonian. Okay, so there is so the energy separation between the energy separation between the levels is same. Okay, I'll show you it. I'll show you by figure. Like before perturbation, this was the case. Okay, this is first energy level, ground state h cut omega, half h cut omega. This is 3 by 2 h cut omega, and this is 5 by 2 h cut omega, right? Before perturbation. So we can see the energy separation between the energy level is h cut omega, or this one is also h cut omega, right? Similarly, and for this case, after perturbation, after applying electric field, this will be the case. The energy decreases, but this is h cut omega by 2 minus q square e square upon 2k, and so on, right? So we can see the energy separation between level is same. Okay, so but energy decreases, right? So I have shown you in the diagram, right? I hope you understood it. Next, we'll find perturbed solution. Okay, so now next point is, let me just check. Okay, my internet is working fine. Okay, now perturbed solution. Perturbed solution. We'll find perturbed solution for this. Okay, so we know this is h equal to h naught plus lambda p, lambda hp, right? So this is the Hamiltonian after perturbation. Okay, or we can write h equal to, for this simple harmonic oscillator, px upon 2m plus half m omega square x square plus qex, right? Qex, lambda is also here, qex, right? Or not qex, just qex, right? So this is the Hamiltonian qex, and this is the total Hamiltonian, right? Also here we can say here where hp, value of hp is, from if you compare these two, hp is x. Okay, value of hp is x, value of hp is x, and value of lambda is, very important. Value of lambda is QE. Okay, so this is lambda and this is HP. Okay, you need to understand. So we are going to get perturbed solutions. Okay, so this is the one. Next, now we have got these values, right? So lambda is QE, HP is X, and this is the actual Hamiltonian, right? Before perturbation. 12. Now we will find the zeroth order solution. Okay, similarly zeroth order solution, zeroth order solution, zeroth order solution. So that is also we know, that is called known solution. We know it, right? Known solution, known solution, known solution. Okay, so that is we know, that is h cut h naught psi naught, h naught psi n naught, h naught psi n naught equal to en naught psi n naught. Okay, or we can write it, since we know en naught value, we know, right? Known solution, that is n plus half h cut omega, right? And psi n naught also we know, that is we know for simple harmonic oscillator, right? I have already explained it in my previous lectures of quantum mechanics, when I explained simple harmonic oscillator, simple harmonic quantum oscillator. Okay, so this we know, alpha upon 2 to the power n into n factorial root pi into hn x, that is Hermite polynomial, right? And e to the power minus alpha square x square by 2, right? This we know, right? So for this is for actual Hamiltonian, right? So we know the energy, we know the energy of the system, ground state energy of the system. Also we know the ground state wave function, right? Or if we calculate it, we put value of alpha, right? This I have already explained in my previous lecture of simple harmonic oscillator. You can check it. Okay, so this is this psi n 0 is going to be, I'm writing directly. So this is m omega upon phi h cut to the power 1 by 4 e to the power minus m omega square x square by m omega square x square by 2h. M omega, my apology, m omega x square upon 2h cut. Okay, and we know value of alpha is m omega upon h cut root. Okay, this we know. So you can check my previous lecture of quantum harmonic oscillator, you will get all these details. Okay, so this is the ground state wave function and ground state energy. Okay, this is known, we know it. Next, first order correction. So first order correction, first order correction. Okay, first order correction, that is en1, that is that we know, right? Psi n 0 HP psi n 0, expectation value of this, right? This we know, first order correction. For in case of harmonic oscillator, this is going to be n x. Okay, so state is this one, right? So this is n x, because HP is x, right? I have already explained in earlier. So, and this is n. We can write like this, right? For simple harmonic oscillator we are talking about. So and we know the value of x, right? Expectation value of x and value of x, that we know. This is the operator, x operator, and value we know, that also I have explained in my previous lecture of quantum harmonic oscillator. You can check it. So this is root h cut upon 2m omega, 2m omega, h cut upon 2m omega. Okay, n into a dagger plus a n, right? This is the one. So this is going to be, that is the first order correction in the energy, that is going to be root h cut upon 2m omega. We will simplify it, right? So this is going to be, if this is going to operate with this and this, right? A dagger. So for a dagger, we already know that is, I'm going to write here as well. So it is raising operator, right? If it operates with this, it becomes root n plus 1, n plus 1. State, there is a increase in state by 1, right? This one. And a n, if you operate n a with n, that I hope you know it. Okay, so we will use here. So this is going to be root n plus 1, n into n plus 1, okay, plus root n, n into n plus n minus 1. So this we know, right? The states are different, right? N minus 1. It means this value is 0, this value is 0. So first order correction in the first order correction of harmonic oscillator is, this is 0, this is 0. Okay, so an1 equal to 0. First order correction is 0. Okay, for the case of simple harmonic oscillator. Next we'll find second order correction. Second order correction. Second order correction, right? Second chord. So also, so we can write here that for 1D harmonic oscillator, the first order correction is, in energy is 0. Okay. Next, second order correction. Second order correction formula we know, that is En2. That value is sigma m not equal to n, right? M not equal to n, and that is mod square of psi m naught hp psi n naught upon en naught minus em naught, right? Yeah, this is the one. This is the formula. En2 equal to sigma m naught equal to n mod square of psi m naught hp psi n naught upon en naught minus em naught. Okay, so now we'll put the value. So this is going to be, so value of hp is, we know, right? So that is x, right? So this is going to be, and this is mod square, right? So this value is going to be h cut upon 2m omega, okay, sigma m not equal to n, and this is going to be mod square of m a dagger plus a, value of x we have put. Okay, so here in place of hp I'm going to write x. This is hp. Okay, so a dagger and then n mod square upon en naught minus em naught. Okay, so this is going to be h cut upon 2m omega sigma m not equal to n, m not equal to n, and this is going to be, we'll solve it, right? So this is going to be root n plus 1 m into n plus 1, because it's a raising operator. I have already told this formula, right? We have used it, plus for this is, it's going to be root n m into n minus 1. This is mod square, simple calculation guys, mod square upon en naught minus em naught. Okay, so next it's going to be h cut upon 2m omega, and this is sigma m not equal to n and m equal to n plus 1. Because why m plus 1? If n if m will be n plus 1, right? So in that case, this n plus 1, this value is going to be 1, right? Similarly, n equal to n minus 1, right? M equal to n minus 1. Okay, so value of m is n plus 1, right? So this is going to be, so now we'll put it, so it is going to be, if you put that, if put this value, so it is going to be sigma m not equal to n, this is going to be n plus 1, the mod square of this, and root n plus 1 mod square is n plus 1, and this m, in place of m we'll write n plus 1, so this value will be 1. Similarly, this value will be 1 here, m value will be n plus 1, because we have taken this m equal to n plus 1, right? So this is going to be n plus 1 minus h cut omega, okay, plus n upon h cut omega. How? This one, here we have put in place of m we have put n plus 1, right? So n plus 1 is higher energy, so this is minus, right? So this value is going to be minus h cut omega, difference is going to be minus h cut omega, right? Okay, so now this value is going to be, that is second order correction in the energy, that is going to be h cut upon 2m omega, h cut upon 2m omega into, will take 1 upon h cut omega common, okay, 1 upon h cut omega common where we are going to take, and this is going to be n plus 1 minus n, minus is there, right? Minus n minus 1 plus n, okay, and one n will get cancelled, right? So en2 value is going to be minus h cut will get cancelled, right? Minus 2m omega square. So this is the value, 2m omega square, 2m omega square, okay? So en is going to be energy, the energy after perturbation is going to be en naught, ground state energy, actual energy, upon en1 plus en2, right? So en naught, we know this value, so this is going to be en equal to n plus half h cut omega, right? N plus half h cut omega, because this is the actual the perturbation before, so this is the energy before perturbation, right? And en value we know for a harmonic oscillator, and this is 0, the correction in the energy, in the first order correction in the energy, that is 0, and second order correction in the energy value is this, right? So we'll put it plus 0 and minus this is going to plus lambda square, second order correction, lambda square into value of En, right? So this is going to be minus 1 upon 2 m omega square, right? This value we have got. So this is going to be E n plus half h cut omega minus lambda value we know, that is QE. Lambda square is Q square E square upon 2m omega square, right? This is the one. So this is the energy of simple harmonic oscillator, right? Which I have already explained earlier as well. Here, right? This one. So by Perturb solution, we have got these solutions, right? And we have put the value and we have got it. Okay. So this is the one. Okay. Next point. Now first order correction in the wave function also we are going to find. Okay. So first order correction first order correction in wave function. Okay, in the wave function. First order correction in the wave function. So this we know, right? Psi n value I have already explained. Psi n1, that is sigma m not equal to n. Okay, mod of psi m naught hp psi m naught hp psi n naught, right, upon en naught minus em naught okay, and get psi m naught. Okay, so this is the formula for the first order correction in the wave function. Now we are going to find or calculate the first order correction, okay, in the wave function of simple harmonic oscillator. Okay, so we'll write it. This is going to be psi n1 is going to be, that is going to be sigma m naught equal to n. So we can write psi m naught, this value is QEX, right? This is the value of perturbed part, QEX, then psi m naught upon En naught minus Em naught, and this is psi m naught, right? Psi m naught, this is m. Okay, psi m naught. So we'll further simplify it. So this is psi n1 is going to be QE will take common, okay, and value of x will remain there, and value of x we know, right? Expectation value, how to find it? So that is root h cut upon m omega, 2m omega will be outside, and m not equal to n, and this is going to be mx, this is n. mxn, right? mxn upon en naught minus em naught, okay, and minus this is going to be m. Okay, so I'll proceed further. So this is going to be psi n1, this value is going to be QE into root h cut upon 2m omega, okay, sigma m not equal to n, will put the value of x, okay. This we have taken common, here it's going to be a plus a dagger, guys, okay. I have not written, so instead of value of x I have to write a dagger, and this will be out because value expectation value of x we know. So that is going to be sigma m into a plus a dagger, a dagger plus a, this is n upon em0 minus em0, that is en0, okay, this is en0 and m. So this value is going to be QE root h cut upon 2m omega, okay, sigma, so we'll write it separate, okay, sigma m not equal to n, and this is m a dagger n outside m upon en naught minus em naught, then plus this value is common, okay, sigma m not equal to n, m a into n outside m upon en naught minus em naught, okay. So this value is going to be QE into root h cut upon 2m omega, okay. So this value will solve it. So this is going to be sigma. Now a dagger will open it, right? So this is going to be m not equal to n, this is root n plus 1, okay, and this is going to be m n and outside m, right? And similarly here this is going to be root n m into m minus 1. We have made some mistake, this is mn, right? Yeah, that's correct. So this is n plus 1 and this is n plus 1, okay, n plus 1, and this is n minus 1, and outside m upon en naught minus em naught upon en naught minus em naught, okay. So now we'll solve it further. So this is going to be psi n1, first order correction in the wave function, and that is going to be QE root h cut upon 2m omega, okay, and this is going to be sigma m not equal to n and m equal to n plus 1, okay. Why we are going to m equal to n plus 1? Then this value will give 1, right? And here we'll do m equal to n minus 1, then this value is going to give 1, right? First state. So this is going to be, this value is going to be then root n plus 1, root n plus 1, this one, root n plus 1 upon minus h cut omega plus, this is going to be and there is one, there is state m is n plus 1, okay, this is n plus 1 plus root n upon h cut omega, this is n minus 1, okay. So this is going to be QE upon h cut omega will take common h cut omega root h cut upon 2m omega, okay, and this is going to be root n into n minus 1 is the state, okay, minus this one root n plus 1, root n plus 1 into state is n plus 1, okay. So this is the first order correction in the wave function, okay. So QE upon h cut omega into root h cut upon 2m omega, and then n into root n into n minus 1, this is the state, minus root n plus 1 into n plus 1 state, okay. So this is the first order correction in the wave function, guys. I hope you understood it. Next point. Next point is very important points are there, okay. So I'm going to so I'll start with the question. Question is, find out, I'll tell you the trick, okay. Find out first order correction in the energy of perturbed Hamiltonian. Perturbed Hamiltonian of 1D harmonic oscillator. 1D harmonic oscillator, okay. The question is, find out first order correction in the energy of perturbed Hamiltonian of 1D harmonic oscillator, and perturbation is given, Hp is given, that is alpha x square, this is given, okay. So simple. So first order correction we need to find out, right? So En1, and that is going to be very simple, right? The expectation where this is a harmonic oscillator, so this is going to be n HPN, right? So this is going to be n HP, we know that is alpha x square, and first order correction, okay, and n is the state for the 1D harmonic oscillator, right? And so alpha will take outside, and that this is going to be n x square, and expectation value of x square I have already explained in my previous lecture of simple harmonic oscillator, right? This is expectation value of x square, that is n x square n this, right? So this I have already explained, and this value is, we know, that is this one, h upon m omega n plus half, right? This is the one. So for that, so now we have to find out for the ground state, right? So this is going to be so we'll put the value. So this is going to be alpha, this value is into h cut upon m omega into n plus half, right? And for the ground state, n is 0, right? First order correction. First order correction in the energy of perturbed Hamiltonian, right? So for ground state, first order correction in the ground state, that is going to be n equal to 0. If you put n equal to 0, the value is going to be alpha h cut n will be 0, right? 2m omega, alpha h cut 2m omega, right? Right. So, the alpha h cut upon 2m omega, right? This is the first order correction for the Hamilton, for the first order correction in the ground state of Hamilton, perturbed Hamiltonian of 1D harmonic oscillator, and perturbation is given this, right? Very simple. Next question. If it is asked, if same question is asked, like if you have been asked for first order correction, in the first excited state of of harmonic oscillator, then En1 is going to be this one, which we know En value, right? This is h cut upon 2m omega, alpha is also there, right? N plus half, right? This is the one, this one, right? So now for first order, now for that is first order correction for the first excited state, that is for that n equal to 1, for it, for that n equal to 1, right? And then first order correction in the first excited state is going to be alpha h cut upon 2m omega. This value is going to be 1 plus half, right? So this is going to be 3 alpha h cut upon 2m omega. Okay, so this is the ground state, and this is the first order correction in the first excited state. For that n equal to, we'll take n equal to 1, and first order correction, first order correction in the ground state energy, n equal to, we'll put n equal to 0. Okay, because for ground state energy n equal to 0, for first excited state n equal to 1. I hope you understood it. Now I'll tell you the trick. Okay, so trick. So trick is this we know, that is expectation value of x square, that you need to note down. Okay, that is h cut upon m omega n plus half, right? You can easily find out for any state, right? And also expectation value of any odd power of x. Okay, any odd power of x to the power 5, x to the power 7, x to the power 3, or any odd power. Okay, that is going to be 0, because we know expectation value of x is 0, right? So any so expect, for simple harmonic oscillator case, expectation value of x cube, any odd power of x is going to be 0, guys. Okay, this you need to know, note down and memorize. Okay, and if so this one, and for if you want to know the trick, right? Expectation value of x to the power 4, this you need to know, this formula you need to know down, that is h cut upon 2m omega, h cut upon 2m omega whole square, h cut upon 2m omega whole square, 6n square plus 6n plus 3. Okay, so you can easily find out the expectation value of x square, right? This, if you know this formula. Similarly, expectation value of e to the power 4, e to the power 4, that momentum, right? And that is going to be uh, m omega h cut by 2 whole square, m omega h cut by 2 whole square, and this is going to be 6n. So this is going to be 6n square plus 6n plus 3. Very important. So you can easily find out the expectation values. Okay, that means if you know that, you can easily find the first order correction in the energy, right? Because first order correction means expectation value you need to find out, right? So you can easily find out the first order correction if you know these tricks. Okay, very simple, right? You need to note down. Okay, next point. Next question is, Next question is, like, question is given, HP equal to beta x cube. Okay, so you need to beta x cube is given, and you need to find out, this is 1D harmonic oscillator. You need to find out first order correction in the ground state energy of harmonic oscillator. Okay, 1D harmonic oscillator. Okay, so you can easily find out En1 first order correction in the ground state of simple harmonic oscillator of which is in 1D, right? That is going to be N beta. So this is very simple, right? By trick we can easily solve it, so we don't have to do calculations. Okay, this is N equal to beta x cube N, right? So beta will take common, and that this is going to be N x cube, and expectation value of x cube we know, right? That is 0, or power of n for simple harmonic oscillator, right? So this is going to be 0. Directly we can find out. Okay, and the power 4. Next question. Okay, for that you need to find out first order correction of ground state energy of 1D harmonic oscillator. Very simple, right? So En1 first order correction in the ground state, that is going to be this one, simple, n gamma x to the power 4 n, right? So what we can take gamma outside, and n x4 n, right? Now x4 we know expectation value of x4. You just need to note this one, this formula. So this is going to be h cut upon 2m omega whole square, and 6n ground state is 6n square, means 60 plus n, that is 0. This one 6n square into 6n. Okay, into 6n square plus 6n square plus 6n, same thing. Okay, 6n square plus 6n. So this is going to be 6n is 60 into 0, right? And plus 3 is there, right? 3. So this is going to be gamma is here, right? Gamma. So this is going to be gamma 3 gamma 3 gamma h cut square upon 4 omega square. So 4m square omega square, right? Very simple. Okay. This is the answer. Very simple. If you know this trick, you can easily find out first order correction. Okay. You just need to find out expectation value, and then you need to put it. So these are the tricks. Okay. Next question. Next question also I will solve it by trick, so you can also solve it with proper method. Okay, so question is, time is already over, but I'll finish it. Question is, find out first order correction in energy of 1D infinite potential box. You need to find out the first order correction in the energy of 1D infinite potential box. Okay, so we have been given this one. This is 0, this is L by 2, and this is L. Okay, and this is V naught. Okay, so for this you need to find out perturbation, and HP is given, that is perturbation is given, V naught when x is between 0 to L by 2 and 0 when 0 otherwise, okay, 0 otherwise. Zero otherwise, okay, this is the potential which is given, right? So we can use the proper method of this, right? 1D harmonic oscillator one, sorry, for infinite potential box, we will so we know the ground state wave function of uh, infinite potential box, right? Then we'll find expectation value like psi no, this one, like this expectation value is psi n naught hp psi n naught, right? Ground state wave function, and we can find out. But here I will tell you the trick. Very simple. So we need to find out the first order correction for in this ground state. First order correction in the energy of 1D infinite potential box for this one, right? So it's very simple. So what we are going to do, we'll find the volume at L equal to 1, right? Volume of this part at L equal to 1. This is a trick, guide. Okay. So this is I mean to say, sorry, my apology. This is area of this part at L equal to 1. So area, this is the width, right? This is L by 2. This is V naught height, right? In the ground state energy, it's going to be V naught into L by 2 at L equal to 1, right? So this is going to be V naught by 2. This is the answer, guys. You can easily find out, right? This is a trick. Area at L equal to 1. Simple. For second, one more question I'm going to give. This is question. This is given like this. This is the one, okay? This is V naught. This is L by 4 and this is L, okay? This is after perturbation, okay? This is infinite. This is also infinite potential box, okay? 1D potential box. So here you can check. So how you are going to get it? So you can use that proper method, right? So first you will find the wave function, right? Wave function of ground state of the 1D infinite potential, right? And then you can find the expectation value. It's a lengthy process, so easily you can solve it. So very simple. Area of this part at L equal to 1. So this height is V naught, right? V naught into L by 4 at L equal to 1. So this is going to be V naught by 4. Okay, very simple. So how the trick is, area of perturbed path, or we can write perturbed area perturbed, perturbed area at L equal to 1. Okay, in place of L we'll write 1. This is trick. You can easily solve it, guys. Okay, perturbed area at L equal to 1. So this is perturbed area, that is En1, right? Perturbed area, that is this this width into this height at L equal to 1. In place of L we will write 1. Very simple question, guys. Okay. Okay, guys. So well, time is already over. Okay, guys. So before ending the class, I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my free live classes which are going to help you to crack the exams related to physical science. Okay, okay guys, thank you so much. Bye now.